Good evening and welcome to the University of Tasmania's Island of Ideas public talk series. Tonight's event is brought to you in honour of National Science Week and in collaboration with the Australian Antarctic Program Partnership. My name is Ed Doddridge and I'm a physical oceanographer here at the Institute for Marine and Antarctic Studies. Like many people who work in this building, my work focuses on the Southern Ocean and Antarctica and its role in our climate system. For tonight's special Science Week event, we are broadcasting live to the world from Lutruwita, Tasmania, Aboriginal land, sea and waterways. In recognition of the deep history and culture of this island, the University of Tasmania wishes to acknowledge the traditional and original custodians of Lutruwita, Tasmania, the Palawa and Muanina peoples. We have gathered to share ideas at the Institute for Marine and Antarctic Studies on the waterfront of Timtuli Minanya, the River Derwent, as they once gathered to share knowledge, stories, and culture. Tonight, we will discuss how the natural world works with us to combat one of our biggest modern existential threats, climate change. And as we do this, we reflect on those who came before us and lived in harmony with this land for thousands of years. We pay our respect to elders past and present, and those who were forcibly removed from the lands and never made elder status. Theirs is a history of people who observed the sun and stars to inform navigation, calendars, and weather patterns. Their knowledge, handed down through generations, predates the works of thinkers in Babylon, Greece, or the Age of Enlightenment. We stand for a future that profoundly respects and acknowledges Aboriginal perspectives, culture, language, and history, and the continued effort to fight for Aboriginal justice and rights. On behalf of the University of Tasmania, I would like to express a sincere welcome to you all tonight, whether you are joining us from your cosy home or you've come to join us in person. It is a delight to share the work of these amazing speakers with you and some of their helpers tonight. The Island of Ideas series began in 2020 as a way of connecting with our community and ideas while we were unable to host face-to-face events. Sharing knowledge is an important part of our university culture. The Island of Ideas program continues to broadcast these events across the world in the hope that we can connect the ideas and people of Lutruwita, Tasmania to a global network of collaborators and thinkers so that we can work together to create a better future. The topic of our discussion tonight is Unsung Heroes, Southern Ocean versus climate change. We are all experiencing firsthand the impacts of climate change. This is a figure known as the climate stripes, and it shows the global average temperature change from 1850 right through to this year. Blue means cold, red means hot. It doesn't take a lot of interpretation to realise that we're in a rapidly changing climate. In recent years, not only have we seen devastation caused by floods, fires, and other climate-related disasters, we have also seen this dramatic increase in temperature. Even though we tend to talk about it in terms of the atmospheric temperature, climate change really is an ocean phenomenon. That is where the vast majority of the heat and carbon end up. So approximately 90% of the heat that has been trapped on the Earth by climate change ends up in the ocean. The ocean also absorbs approximately a quarter of the CO2 that we emit into the atmosphere. And the Southern Ocean is at the heart of the global ocean. Now, this is a fairly unusual map projection because instead of cutting through the oceans in order to spread the world out flat, we have cut through the continents. And what you can see here is that we have one global ocean. We talk of it in terms of the Pacific or the Atlantic, but they're all connected. And the place that they connect is the Southern Ocean. This is why the Southern Ocean is such a crucial ocean to understand, and why it is crucial to understand it in order to be able to predict climate change. Now, sea ice is crucial to the connection between the atmosphere and the ocean, and this is the annual cycle of sea ice forming and freezing in the wintertime and then melting away in the summer. As it forms and freezes, it releases a cold, salty brine that sinks down into the ocean abyss, filling almost half of the volume of the global ocean. As it moves northwards away from Antarctica, It takes with it oxygen and nutrients that sustain ecosystems and life throughout the global ocean. Climate change is not just a challenge for humans and the regions where we choose to live. It is a global challenge. And some of the largest impacts are being seen in the Southern Ocean and around Antarctica. This is a plot of sea ice extent anomalies from Antarctica. And you can see that in recent years, there has been large negative anomalies. There has been much less sea ice than expected. This is particularly true this year, where we have set multiple records almost every day for a new record low in sea ice. Today, we will learn about some of the extraordinary plants and animals of the Southern Ocean and how they are lending us a helping hand, or flipper, in our quest to understand and solve the challenges of climate change. Joining us to discuss our unsung heroes of the Southern Ocean are three experts: Dr. Tamara Schlosser, Dr. Clive McMahon, and Dr. Sophie Bestley. One of the ways that the Southern Ocean helps us with climate change is absorbing CO2. And one of the mechanisms for this CO2 absorption is called the biological pump. The perfect person to tell us about the biological pump is Dr. Tamara Schlosser, our first speaker tonight. Now, Dr. Schlosser is a seagoing oceanographer who explores the connections between the physical environment, like winds and currents, and the biological environment, the things that live in the ocean. She is currently a research associate in Marine Ecosystems Remote Sensing at the University of Tasmania's Institute for Marine and Antarctic Studies. Her focus is on the variability of photosynthesizing organisms, phytoplankton, that make up the base of the food web and play a critical role in the biological pump of carbon from the atmosphere to the deep ocean. Please give a warm welcome to Dr. Tamara Schlosser.
So I'm going to talk to you today about the role that the Southern Ocean has in removing carbon dioxide from the atmosphere. Okay, so you might be familiar with how carbon dioxide is removed on land. And so we start out with carbon dioxide in the atmosphere, and it is taken up when plants photosynthesize, turning it into biomass. Then some of this carbon is re-released into the atmosphere at night when the plants respire. And then when the plants eventually die, a lot of that carbon is re-released into the atmosphere via decomposition, and some of it might enter the soil. And by doing so, it might not reappear in the atmosphere for a long time. So you're probably familiar with the importance that our forests have on the land. For example, the Amazon forest alone accounts for 1/4 of all of the CO2 that's absorbed on the land. And so what I hope to do today is to convince you how equally important our marine ecosystems are. So the marine system, again, starts with our atmospheric carbon dioxide, but first it needs to enter the ocean. And so it does this via what we call the solubility pump. So it describes how carbon dioxide dissolves into the water, combines with the water molecules to produce carbonic acid, as well as bicarbonate ions, and hydrogen ions. So 90% of the carbon is actually in this bicarbonate ion, and it's the presence of both the carbonic acid as well as the hydrogen ions which makes the ocean more acidic. So this solubility pump, which removes carbon dioxide from the atmosphere, also makes our oceans more acidic. But this process is temperature dependent. So the colder the temperatures get, the more carbon dioxide can dissolve in the water. And this is why our polar regions are so important, because the waters there are colder, where the waters in the Southern Ocean are about 10 degrees or lower. And so our polar regions have much more importance when it comes to removing carbon from the atmosphere. But in addition to the solubility pump, we also have plant-like organisms in our ocean that can also remove carbon. And so in the ocean, carbon dioxide is taken up by photosynthesizing organisms called phytoplankton, which in Latin means plant drifters, because they're very small and have very little ability to swim, if any. Now, these come in a wide variety of shapes and sizes. So some you can see here are circular, others are long and thin, and some look like they're one large organism, but are in fact a collection of smaller organisms that are one colony. And so just like plants on the land, these organisms respire at night time, releasing carbon dioxide back into the water. And then this carbon dioxide can also re-enter the atmosphere. So it's not a permanent one-way sink of carbon. Then there are herbivores in our oceans which take up carbon. So for example, krill is a dominant species in the Southern Ocean. And so in this way, carbon can move up the food chain into different organisms. And then as plants and animals die, we have this downward carbon flux into the deep ocean. But before I talk about this carbon flux downwards, let's talk a little bit more about phytoplankton. Okay, so Ed's already shown us one image of the beating heart of Antarctica and the variability in sea ice. And so you can see this again in this animation with the extent of sea ice shown in white being largest in the winter and smallest in the summer. Then the colour here is showing us the phytoplankton concentration, blue being a low value and red being a very high value. And so you might be able to notice that as that sea ice retreats after the winter, so going into spring months, there is a huge increase in biomass in our oceans, a very rapid increase that we call the spring bloom of phytoplankton. And these concentrations are so large that they visibly change the colour of our ocean. So these are microscopic critters that are so high in concentration that they're actually changing the colour of our oceans. And in fact, if we compare photosynthesis on the land versus on the ocean, they're about equal. So photosynthesis is equally as important on the ocean as it is on land. But of all this biomass, 1% or less of it will eventually sink to the seafloor and be locked away for millions of years. The vast majority of this biomass will re-enter the atmosphere or into the carbon system eventually. However, how long it takes to re-enter the system is dependent on what depth it sinks to. So if the carbon and the phytoplankton biomass stay in the upper 100 metres, say, then it might be a decade before it's back in the atmosphere. But if it's able to sink to a depth of, say, 1,000 metres or more, this might mean a millennia before that carbon is back in the atmosphere. And so this isn't to say that our biological system means that we don't have to worry about this carbon ever again. It just means it gives us more time before we have to worry about it. And hopefully by then we will have developed methods to sequester carbon. So I'll be talking about three main processes that can remove carbon. Oh, there we go. So first of all, I'll be talking about the gravity pump. So we have this dead plant and animal material as well as fecal pellets, which is poop. And all of this sinks into the deep ocean, becoming what we call marine snow. So I'll let you enjoy this video of what marine snow looks like. All right, so marine snow falls relatively slowly, so about 100 metres per day, although it can be as slow as a metre per day or as fast as 500 metres per day. By comparison, ocean mixing can occur very rapidly, and it describes the motion of our oceans. So our oceans are exposed to the winds as well as the tides and the sun, and all of this can result in energetic motion, which can force the carbon downward into the deep ocean. So I'm going to show you a video of a laboratory experiment from the University of Melbourne where they have released dye on the surface of the water and then they move a metal plate at about 1 metre per second. And I'm going to pretend this metal plate is equivalent to a storm coming through with very energetic winds blowing on the surface of the water. And so I'm going to pretend this green dye is phytoplankton, which is pretty realistic given that most phytoplankton are unable to swim. And so if the fluid forces them downward, then that's where they go. And I'm going to pretend that as we go down into deeper depths in the water, this is equivalent to getting deeper in our ocean, getting further away from the well-lit surface of the ocean into regions where there's no light and therefore they can't survive. All right, and we can describe the motion of this fluid using this advection diffusion equation. So it's a neat example of how calculus and maths can help us understand our environment. And as you see the dye getting pushed deeper and deeper in the water, this is equivalent to how a storm comes in through the ocean and you have these organisms happily living in the upper ocean of the water that are forcefully moved down rapidly. In a couple of hours, they might be as deep as 300 meters depth. So ocean mixing describes the physical motion of our oceans, while the migrant pump describes the biological motion of our oceans. So there are many organisms like fish living in our oceans that move around, and as they move, they also move the carbon in our oceans and can move it downward. So the well-lit upper ocean might be great if you're a phytoplankton because it's nice and well-lit and you can photosynthesize. However, if you're a fish, it's maybe not so good because in the well-lit upper ocean, you are visible and you might be eaten. And so what many organisms do is they swim to the deep ocean during the day to avoid predation. So they might be anywhere from, say, 200 meters depth to even 1,000 meters deep. And then during the nighttime, they will swim back up to the surface of the ocean so that they can eat as much as they want because most of their food that they want to eat is near the surface. And so in this way, they swim up to the surface of the ocean during the night, eat as much as they want, and then maybe swim back down to a depth of 1,000 meters where they might poop. And so overnight, we have a 1,000-meter movement of carbon. So 3 different processes here that relies upon the biological carbon pump, all happening at different speeds. And remember that the deeper we get, the longer it is before that carbon reappears in our atmosphere. But how is this changing in the future? Well, there's a lot of different processes and variability that I'm showing here. And the problem is that the biological pump of carbon is complicated and involves many different systems interacting. But let's look at a couple of examples. One being that the Southern Ocean is predicted to get more windy. And so this means that there might be more ocean mixing. So as long as phytoplankton are still able to thrive, maybe there's an increase in the downward carbon pump. It's also warming, so that might be good for phytoplankton because they might like it a little bit warm. But more concerning is the fact that the solubility pump of carbon is temperature dependent. So if it does get warmer, unfortunately, it will mean that there will be less carbon dioxide dissolving into the water. And so this is quite concerning. Additionally, there are changes in the ice shelves, which is very concerning and other speakers will talk about more, as well as the decline in marine life. And so that migrant pump, which does rely upon our life being in the ocean, can get severely impacted if we overfish and if there's a decline in important species. And so it is complicated how the biological carbon pump will change. There are, of course, technological solutions, for example, carbon sequestration, where they're looking at artificially injecting carbon dioxide below the ground. So this is great, and I am definitely an advocate for technological solutions. However, I definitely think that carbon emissions need to get removed from the equation. We need to focus on removing that carbon dioxide, not releasing more. But these solutions will be expensive. So as we think about this existing system we have, the biological pump of carbon, we need to remember that this is a free and natural system. So I hope I've convinced you today that this system is worth protecting. And we also maybe should consider how we might cautiously promote this existing Southern Ocean biological pump of carbon. Thank you.
Wonderful. Thank you so much, Tamara, for an amazing talk. Who would have thought that such tiny, tiny creatures could change the colour of the ocean and play such an incredibly important role in our climate system? It always amazes me the number of roles that the ocean can play in our lives. Food source, place to go surfing, and also carbon storage. Now, our next speaker tonight is Dr. Clive McMahon, based at the Sydney Institute of Marine Science, and he leads the Integrated Marine Observing Systems Animal Tracking Facility. We're delighted to have him join us tonight to share his more than 30 years of experience working with elephant seals. Elephant seals are the ultimate divers, travelling long distances and diving to depths of up to 1,500 metres below the surface. These animals are crucial to gathering knowledge about the Southern Ocean's role in climate change and the global system more broadly. Please join me in welcoming Dr. Clive McMahon.
Right, thanks, Ed, and thanks, Tamara, for introducing the subject so well and talking about heartbeats and and the lungs of our ocean, and in fact, the lungs of the world. I'm delighted to be here. I'm delighted to see so many folks here. I'm going to just give you one slide. And the slide I'm showing up here is a picture of elephant seals, mainly elephant seals, swimming around in the Southern Ocean. We equip these elephant seals with really sophisticated state-of-the-art equipment that measures temperature, conductivity, and depth. It also measures time and some other bits and pieces. But the key things that we're really interested in is temperature, salinity, so conductivity, and then the depth, because this tells us about where heat is being stored and how that heat is being moved around in the ocean. Ed gave a fantastic introduction to what elephant seals can do. They regularly dive below 1,000 metres, but will dive below 2,000 metres. So that's an incredibly long way down, and they do this through a number of physiological adaptations, and we can talk about those maybe in the discussion. But what I really want to talk about here is I want to talk about the role that elephant seals are playing in helping us understand what happens in the Southern Ocean. So we've heard about temperature, we've heard about density, which is heat, and we've heard about carbon. Carbon is one of the key things we're trying to measure and understand. And elephant seals, on the instruments that they are carrying, can also measure fluorometry. And that fluorometry tells us about the productive and unproductive parts of the ocean. And then we can link that to the animal's behaviour. So we can identify where the good spots are in the ocean and where the bad spots are in the ocean. And not everywhere is equal. You would have seen on Tamara's little image of the carbon coming and going in various areas in relation to the sea ice. Now, the fantastic thing about elephant seals, on one level, I kind of always want to start these talks by saying, elephant seals are perfect. This is another talk on why they're perfect. Now can we have a discussion about that? But a little bit more information. So the great thing about the seals is they head down to Antarctica and they stay there during the winter, where they dive to depths, they collect this fantastic information, and they have to come to the surface every 20 minutes. And that information is then transmitted via a satellite constellation, Argos, in real time. So we can see what's happening in the ocean. Literally, now we could log into some of our system and see what was happening 6-8 hours ago. So that information we make available to everybody to help understand what the Southern Ocean is doing, how it's doing it, and where are the important parts. Now, to be able to make any kind of realistic prediction on what's happening in the ocean, we need long time series. And so that's why I'm playing the little animation behind us. This is capturing information over about 10 years. And you can see the seals. Each year we go to various places. We attach the instruments to them. The instruments are quite small. There's an example that Sophie's brought in, and I'm sure she's going to talk a bit more about that. And the instruments will then stay on the seal for about 10 months, and then either we remove them or they fall off naturally. The instrument is just stuck to the animal's hair, and they weigh about 500 grams, 560 grams. And the seals we're attaching these instruments to weigh between 5 and 800 kilograms. So they're big animals carrying a small thing. So if you think about your mass, your weight, and how that equates, it's 0.05%, so a small number. So we know that the animals aren't being affected by carrying the instruments, but the information they're collecting is proving vital to help us understand what's happening in the ocean. Now, Ed talked a little bit about dense water. He talked about this really heavy, salty water that's produced in the Southern Ocean. One of the fantastic things about the seals is that as the ice or as the water starts to freeze in the autumn, the seals are down in Antarctica on the continental shelf measuring this. So we can calculate, we can observe how much salt is being extruded. We can measure the density of the water. And from that, we can measure or we can get some idea of the strength of the circulation. So this is the beating heart of the globe. So Antarctica is, in fact, the beating heart, and we need to look after it. If we restrict it, like our hearts, we start getting problems. Heat isn't dissipated through the ocean. Oxygen isn't dissipated. We start getting problems. We're having breathing problems. Eventually, if we don't do something about that, we fall over and have a heart attack. It's not a great situation to be in. We're almost there. Many people are saying we're there right now. And I think the key thing here, and from Tamara's talk too, is we need to start thinking about how we stop putting carbon dioxide into the ocean. Again, the seals are telling us what's happening. We're seeing the changes. We've now been collecting data or information from the southern Indian Ocean for 20 consecutive years. We're starting to see changes in temperature. We see changes in water density. We see changes in heat. This is not good stuff happening. We need to do something about that. The key here is that we can only detect these changes if we do this work long term. Supporting this work is not always easy, but the integrated marine observing system in Australia has proven a lifesaver for all of us. It's been providing funding for the work that we do for the last 16, 17 years. So this is an enormous investment, and I think as Australians we can all be incredibly proud that we have this facility allowing us to do this work. And this is part of a broader group called NCRIS, and they do lots of other things. So there's some other centres of excellence, all doing good things. But I think in the context here, we can be really proud of where we're going. So I'm going to leave it there for now, other than to say that what we're doing in Australia is world leading. As part of our program and as a spin-off of our program, we've created and had endorsed by the United Nations program under UNESCO, a program called IMOS, which stands for the Animal-Borne Ocean Sensor Network, and that is now recognised as an essential observing network around the globe to provide information that we need to understand climate and to understand animal behaviour. Because where this all started, it started from a number of us, biologists, sitting around wanting to know how climate and how the physical environment affects the animals. And then we realised that the animals were actually collecting the essential information we need to understand the oceans, and then how that translates into animal behaviour and animal performance. So thanks very much.
Up to 2,000 metres. What incredible creatures, and helping us by sending back real-time information about the Southern Ocean so that we can know what it was like just 8 hours ago, 2,000 metres below the surface of the ocean. It's incredible to think that we have these helpful explorers sending us back such amazing data from inhospitable and difficult to reach places. Now, our final speaker tonight is Dr. Sophie Bestley, who is a senior lecturer in Quantitative Southern Ocean Ecology here at the University of Tasmania's Institute for Marine and Antarctic Studies. She contributes to the Australian Antarctic Program Partnership through multidisciplinary research interfacing biological oceanography, ecology, and quantitative methods. She uses animal-borne telemetry to gain novel insights into Antarctic and Southern Ocean systems and has participated in 3 polar research voyages. Tonight, she will be telling us about polynyas, the sea ice factories of the ocean, and why they play such an important role in the climate system. Please join me in welcoming Dr. Sophie Bestley.
Thank you so much. What a delight to be here, and thank you to the speakers that have gone before me and laid the scene so beautifully, and thank you for everyone joining us tonight. So my name is Sophie. I work with Clive and the seals quite closely. And what I'm going to talk to you about tonight will just take us even further south. So we've been introduced to the Southern Ocean and the incredibly important role that phytoplankton play. And I'll be taking you to a place called coastal polynyas, which are around the Antarctic coastline. First, I'll explain what they are, because you may never have heard that term before. And I'm looking to answer the question, really, what is the value proposition of studying Antarctica, and specifically these areas? So I hope by the time I finish my talk, I will have shown you how important they are to us and actually life as we know it in the world. First, in their role as sea ice factories, which has been mentioned before. Second, because they're regions that are key for forming the densest waters that fill the ocean deep. And thirdly, because of their role as ocean gardens, where many iconic birds and mammals, whales and seabirds, migrate annually to feed and to get fat. So firstly, what are polynyas? We saw that video showing the annual expansion and retraction of the sea ice. But within that 15 million square kilometres of sea ice, there are holes. Holes close to the Antarctic coastline. And the word originally comes from the Russian, and it means a stretch of open water surrounded by ice. It's an Arctic origin word, and you can imagine it was really important for navigation purposes. So how do polynyas form? There are a couple of different mechanisms, but around Antarctica, they're formed by wind. Katabatic winds blow off the continent and they push ice away, so that the ocean in the winter is getting cold at the surface. It goes to freezing point. Ice forms and the winds blow it offshore. Coastal polynyas form in the lee of prominent features like glaciers or headlands. And so new sea ice can't come in to replace it. And so it means it's an open water area. It can continually create sea ice. So even though they only cover about 1% of the oceans, of the Southern Ocean area, they are producing way more than 1% of the ocean's ice. Actually about 10 to 1. So they're sea ice factories, very cool places, not really an ideal holiday destination. Around Antarctica, there's 13 major coastal polynyas and 8 of them are in our Australian Antarctic territory. So they're literally in our backyard and really important for us to be studying. So as well as being sea ice factories, they're really important for physical and biological reasons. So the physics first, even though I'm not an oceanographer, as Clive and Tamara have said, physics and biology are really intricately linked in these systems. So if we think of the ocean, we go swimming, it's warm on the surface, it's cold below, and that's natural and how things are. But if that was just the way things were, life would be pretty crap on this planet. So I think in Ed's map, when he had blue currents and red currents showing around the world, the blue ones are the deep ones. So in some places, deep water is rising to the surface, and in some places, surface water is sinking into the deep. And polynyas is actually where the dense water is forming. So as Clive said, when ice forms, it's fresh, it drops salt back into the ocean. That makes the water denser and it sinks. So firstly, it goes to freezing point, it's cold, then it's salty. So that makes it the densest water in the world's oceans. It can collect around the continental shelves of Antarctica, and in some places, 4 key places, it spills down the continental slope and it fills 30 to 40% of the ocean deep. And if you remember from Tamara's talk, water that's been in contact with the surface, it's full of oxygen, it's full of carbon. And now that is all going down into the deep, down to the abyssal sea floor and being locked away. So polynyas are sea ice factories, number 1. Number 2, we can consider them the lungs of the deep ocean. But I'm not an oceanographer, I'm an ecologist. So what about the biology? So polynyas, coastal polynyas are also hugely important from a biological perspective. Being open water regions, you think it's cold and dark in winter, but in spring when the light returns, these are the first areas to receive that sunlight. The convection and the overturning of the water column, it stabilizes and it provides a really nice habitat for phytoplankton to start blooming. So these are the ocean gardens. So deep within the pack ice, close to the continent and close to the pole, life is beginning every season. And because the bloom starts there early, it can persist for a very long time. So we have long growing seasons. If anyone's tried to grow tomatoes in Tasmania, you know the vagaries of a short growing season, but coastal polynyas for the poles have a relatively long growing season. And if we think about the biological pump, we've got high productivity in the surface waters, and then later in the season, we've got this deep mixing in polynyas. So actually the carbon and all the nutrients can go down to the sea floor And we can have really biodiverse seafloor communities actually around Antarctica. So very important for connecting the surface to the deep, both in terms of physics and biology. From migrating animals' perspective, I work mostly on top predators and many seals, whales, flying birds like albatross, petrel, they go to these open water areas to feed. So iconic emperor penguins, Adelie penguins, humpback whales. Breeding colonies for land-based predators are often located close by to polynyas because it provides open water access for animals that need to dive and then surface again to breathe. So some species migrate down there seasonally, some are resident year-round, like a Weddell seal. But we can consider the third value proposition of coastal polynyas is as biological hotspots. So these are really high-quality forage habitats for animals that we care about. Obviously, they're incredibly inaccessible places, hard to get to. We have a huge Antarctic coastline. It's 7,500 kilometres long is the Australian Antarctic coastline. We have a marine claim that's 2 million square kilometres, which is bigger than Queensland. And we have 8 polynyas scattered along the length. So impossible for us to get there each season. And extremely expensive if we wanted to take a ship, which really can only get there in summer. So we have to use remote mechanisms. When we think about feasibility, there's a few options. You can put in moorings, but maintaining moorings in a really icy habitat is very challenging, and more than one have been flattened by icebergs. There's one sitting under B9b and may be for eternity. Satellites, like the images we've been seeing, are super important for us understanding sea ice dynamics, but it's really only showing us the surface skin of the ocean and nothing about the subsurface. So floats are really tremendous, and we can put different sensors on those. So projects that we're working on at the moment are really looking at combining autonomous floats and animal-borne ocean sensors to give us really valuable information from these places. As Clive showed, the seals dive deeply, they surface to breathe. They transmit information by satellite in real time, and they give us vital information about the upper ocean structure. And they're quite cheap. Okay, so given what we get from these hard-to-reach places, what does all this information show us? It is one of our most successful long-term programs. It's been running since 2004. I'll give you a few of the major scientific findings that have returned. In 2011, along with mooring data, the seal information showed that Cape Darnley polynya in the East Antarctic Territory was actually a 4th major bottom water source. So once upon a time, textbooks were really focused on North Atlantic deep water, which is very cool, but it's actually not as cool as Antarctic bottom water, which is the coldest and the densest. In 2016, one of the studies was published in the Prids Bay area, and it showed that melting ice shelves from the glaciers is actually impacting the capability to produce dense shelf water and Antarctic bottom water. So has implications for really inhibiting this overturning of the global circulation. More recently, we've had a suite of students and postdocs who are showing that not all polynyas are really created equal. There's different physical drivers for how much ice forms, how dense the water is, how deep it then settles. And there's interannual differences amongst them. From a biological perspective, our work on elephant seals firstly showed that they use these areas through the autumn and winter season specifically. You say, okay, well, maybe they just need to be there to breathe. They need access to the surface. The next study showed that they actually really changed their diving behaviour in these different areas. So in a polynya that's very active and reaches full convection, mixing to the sea floor, The seals actually display a more benthic diving behaviour. So they're foraging more on the seafloor communities and the fish that live there, octopus, and very lipid-rich prey items. Whereas weaker polynyas, they have a diving behaviour that's more in the upper ocean. Our last paper looking at elephant seal ecology was showing, because of the way that they dive, they have a special pattern called drift diving, where it's almost like they're asleep in the water column and they kind of float like leaves. And if they're skinny, they sink passively. And if they're fat, they float passively in the water column. And so you can use that as a tracer to see whether they're doing well or whether they're doing poorly. And a study by one of our PhD students published last year showed that animals that use polynya areas get fatter faster. So they're really valuable foraging habitats for marine predators. So what does all of this mean for our fight against climate change? Hobart-based researchers have really done a huge amount to help us gain new knowledge about these areas, and in collaboration with IMOS, CSIRO next door, French collaborators and other international partners. But actually the future prognosis for polynyas is very uncertain. What will happen in these areas? If it gets a lot windier, it's possible that they will spin up, yet there'll be less ice, there'll be more glacial melt, there'll be higher productivity because the ocean garden is being fertilised by iron from glacial melt. They might shut down. If the upper ocean is stratifying and we can't mix the water column, then overall water gets less dense, there's less bottom water being formed. And actually a study just published a couple of months ago by Kathy Gunn showed that bottom water is contracting in the Southern Ocean in a measurable way. So the latest project that we're launching is building on the success of the existing program, but we're adding extra sensors onto the tags. So we're looking at, like Clive said, actually measuring fluorometry in the upper water column. So we want to be able to see where are the productive areas and what are the physical controls on that productivity. So through fancy biooptics, we can actually back out relationships with light and iron and look at areas that have got high iron from glacial melt or from sediment resuspension versus areas that are iron limited. So it will give us new insights into really how these systems work. So to wrap up, many marine animals, whales and birds have finely tuned cycles in terms of their reproduction and their migration that really rely on these areas. And we really need to have a better understanding of these systems and how they might change into the future. Hopefully you'll understand the value proposition of studying Antarctica and these remote places far from you. And you'll appreciate the fantastic contribution that seals are making. Hopefully you've digested some information about the services provided by polynyas as sea ice factories, as formation sites for bottom water, as ocean gardens. And if you're interested to be involved, I'd like to let you know that there are a lot of citizen science opportunities for Antarctic studies that you can get online and join in regarding penguins, whales and seals. Thank you.
Wonderful. Thank you so much for that, Sophie. I love the image of polynyas as ocean gardens. And although Sophie says they're not an ideal holiday destination, I think if you're a seal who's looking to get fat, it sounds pretty perfect to me. So we've heard that the Southern Ocean contains both the lungs and the heart of the global climate system. Sounds pretty important to me. So with these three talks, we've been learning lots of wonderful new things, and it's time now to move to the Q&A section of the evening. So I'd like to invite the three speakers to come and join me here as a panel. So we'll begin with a question for you, Tamara, from one of our online audience members. What is the impact of increasing CO2 acidity and temperature on phytoplankton and also krill?
Okay, so I guess there's a few aspects to that question. So I guess first, acidity. Well, if you are a critter who has a shell, then the acidity is quite problematic because you are literally dissolving in an acidic ocean. And so the rising acidity doesn't necessarily hurt all creatures, but some are definitely going to be impacted very strongly. And so we may see that there's forms of life that will just cease to exist. For example, coral reefs, hard coral just won't exist in an acidic ocean. And so many phytoplankton species have a shell, and these species may just cease to exist if the acidity is not controlled. What was the other aspect of the question, sorry?
The temperature.
The temperature, thank you. So again, changes in the temperature could benefit some species and be negative to others. There is a range shift that is very easy to see in, say, species of fish. So you start seeing species in regions that you previously wouldn't have. So maybe we'll just see that there's species that would typically be a bit more north that are just ranging further and further south. But it could mean that there's very important species, like, for example, of the ice algae, species that actually live in the ice during the wintertime, that just have lost their niche if there's no ice to live in. And so this might not seem that bad, like, oh, there's a more open ocean because there's less ice, so maybe the net biomass has increased. But what could be quite concerning for something like krill is that there's a shift in the seasonality. So, for example, in the open ocean, we might see the phytoplankton biomass increasing in the springtime, so just after maybe August. However, in the ice, we might see the biomass accumulating a bit earlier in the year, and this biomass is incredibly important to the krill living in the ocean, particularly the juvenile krill, which have a very short time period where they need to be eating, otherwise they will starve to death. And so if we shift the temperature, shift the amount of sea ice, shift the species that we see in this region, it may not be that bad if you're just looking, say, at phytoplankton variability. But when you're looking at the entire system, so how it affects the krill, it can be catastrophic. And so this is really about the sensitivity of our systems and trying to predict how some small change like the temperature could have cascading effects.
It really is such a delicately balanced system. Thank you, Tamara. Now, do we have a question from the in-person audience? Yes, up the back there.
Fantastic talk. Thank you so much. Could you please indicate to what extent you share or conduct with your research with owners of others who have claims to Antarctica from around the world?
Thanks for that question. It's an excellent question. And I think before I answer your question directly, I will say that most of the work that we're doing comes from public funding, and therefore it should be publicly available. And when I say publicly available, I mean everybody. I think IMOS is taking a leading role in Australia in doing this, so the Integrated Marine Observing System. Our philosophy is that all of our data are available to everybody nationally, internationally, and then, I guess across the globe. So the information that the seals are beaming back, like I said, any of you, if you so desire, can log on to the system and you can download that data that's about 8 hours old. And somebody in Iceland can do the same thing, and somebody in China and anywhere across the globe can do that. It's really important that we share data because we're trying to address big questions. These are urgent questions, and if we don't share, we're not going to get to the answers, I'm afraid. So, fantastic question, and I hope that we're setting an example that others will follow and share data. And this is becoming more and more common, both in the physical and also the biological sciences. And I'm not sure if someone else wants to add to that.
Well, I could also just mention, in terms of polar partnerships, working amongst the polar programs is super important. And actually the longevity of the program that Clive and I just spoke about has really depended on collaboration with our French polar program, IPEV. And Clive's also been south with the New Zealand polar program in the Ross Sea. So everybody helps everybody in Antarctica because you never know when you're going to need help.
Absolutely. It's such an important environment to cooperate in. Now, Sophie, our next question is for you from online, from Mads, who says, we would like to be involved in citizen science. How can we do this? Really liked your talk. Thank you.
Thank you. So there's a couple of examples that can spring to mind, but we've obviously over time, like Clive said, science is for everyone and everybody can participate. So school kids in classrooms, grown-ups on your laptops. A couple of the really big programs that have been going in the last few years have been censusing animals. So using satellite images, say, to count seal colonies. And you can imagine that takes a lot of time for people to scan images of photographs or satellite images and say, there's a seal, there's a seal. But actually, a program that was launched out of New Zealand has done exactly that right around Antarctica for Weddell seal populations for the first time. Similarly, in the Australian program, they have camera data on Adelie penguin colonies, and people can join in online and actually help to count animals on nests from cameras. In terms of the seal tagging program, we've done a lot of outreach through the schools and public programs, and I'm currently cooking up ways that we could actually engage more citizen science.
Well, I look forward to hearing the result of that cooking. It's time now for a question from our in-person audience. Up the back, yes.
I'm a retired teacher, and I'm thinking of children in schools in particular who are starting to develop quite severe degrees of anxiety about climate change. And I would believe that what I've heard tonight, I think it's been fantastic, but if you could engage appropriately trained, experienced, good teachers, either through your organisation or through the education, contacting the ministers to get around the country to get something like this started, to have what has been presented this evening distilled into appropriate form for upper primary and upper secondary. And I think it would stimulate a lot of interest, which could be great for the eventual political answers which are going to have to come. Don't focus just on the age group we are here, mid-60s on average, I suspect. You've got to get to the younger generation if we're going to save the world.
Wow, thank you very much for that contribution. Would any of you like to respond?
Sure. Thank you very much. You're absolutely right. And actually, as you exit tonight, if the lights are on, I'd encourage you to have a look at the exhibition that's in the art space at the moment, because it is actually showcasing a bunch of publications, science publications that were written for a journal called Frontiers for Young Minds. And actually, the reviewers for those articles are all aged sort of between 10 and 15 years old. So they go out for peer review, not to other scientists, but to children to say, okay, how digestible is this information for somebody in primary school or just early secondary school? So that's one avenue. Also, University of Tasmania has an award-winning program called Curious Climate, and that has been literally in state schools all around the state. And students in classrooms can write their questions and they get posed and put to an expert in that domain, who then can answer it online in a video or in a letter, and then also return to those schools and be in the classroom and having a discussion with those students who have posed the question. So it's a really powerful way to impart information and really engage with bright young minds who are our future solutions.
Sorry, I might just add to that. Again, I think that's a fantastic question, and Sophie's absolutely right. The children are the leaders of tomorrow. They're also the people who are going to live with the consequences of what we've done. And I'd just like to highlight, as part of this education program, Australia through CSIRO runs a fantastic program called Scientists in Schools. And what this program does is it partners scientists with children and teachers at both primary and high schools. And the idea is to take the science from people like us directly into the schools to get children, get their teachers interested in science, get them interested in mathematics, get them interested in changing the world and fixing up some of the problems that we've created.
Wonderful. Thank you very much. It's exciting to contemplate the next generation coming through to help us deal with these really difficult problems. Now, our next question comes from online, and I think perhaps it's for Clive. It's from Anonymous. Can elephant seals dive to 1,000 to 2,000 meters and then swim back to the surface in just 20 minutes? Did I hear that right? Amazing.
Thanks for that question. It's a great question, because what it means is it kind of gives me license to bang on now for the next half hour about how amazing elephant seals are. Absolutely, they do dive to 2,000 meters, and they can dive to 2,000 meters and return to the surface in 20 minutes. How they do this remains somewhat of a mystery to us, but they do this fairly regularly, and they do it consistently over many years, so that we know that it's not just an artifact of how we're measuring things, it is in fact real. And I'd like to add here, I sort of forgot to mention it when I had the floor earlier on, was that these deep dives that the seals are making are actually helping us map the ocean floor, map bathymetry. And this is a really, really important thing, because it helps us measure and observe where water is flowing on the shelf, and how this warm water that Sophie and Ed were talking about comes onto the continental shelf in Antarctica, how it gets below the ice, and how it affects melting rates. So not only are seals telling us about the physics of the ocean, the temperature, the salinity, the density, the heat content, they're also actually telling us about the ocean floor, because they dive so deeply. And this is a really exciting part of the work that we're doing, that we're going to move on into the future now, is to use these dive depths to map what the oceans are, because it may surprise you, but only 23% of the ocean has been mapped in any detail. And that means that for most of the ocean, we're guessing how deep it is. We're using very clever mathematics to make those guesses, but nonetheless, we're guessing. Thank you.
Absolutely. It's such an incredible contribution from these seals. There was a paper just recently that showed some seals diving, 400 meters deeper than we thought the ocean was at that location?
Well, actually, up to 1,000 meters deeper than the ocean, where we thought the ocean floor was. And they're definitely not using instrumentation, as in heavy digging equipment, to do that. It's because we know so little about where the ocean floor actually is.
Such amazing creatures. Now, in the room, yes, we have a question just here.
As a follow-up, why are they diving so deep? Because you think for food and stuff it'd be up higher. So at 2,000 metres, what are they looking for? Because it's dark and cold and...
Absolutely. I'm going to answer this only partly, because I'm going to let Sophie answer most of that, because it's a difficult question. But they are diving because there is food there. And I think the key thing that we have to remember about seals, this is Weddell seals too, and elephant seals in particular, is that these animals are spending 80 to 90% of their lives below the ocean surface. So they're spending most of their lives in the water. So they're actually divers. Their lifestyle is diving and living below the ocean. That's their sort of natural habitat. And they only come to the surface briefly to do things like breed and molt each year. So what they're doing in the ocean is kind of what we'd be doing in our normal day. You know, someone might say, gee, it's quite weird. Clive goes, in the morning he goes over to have a coffee at Retro, and then he comes back, and then he goes and has lunch at Banjos, and then he comes back and he goes and has a coffee somewhere else, and then, he trundles off to Shippies and has a beer before he goes home. That's kind of a bit weird, he's all over the place. But that's what humans do. We do what we do, and it's unremarkable. And while it's remarkable to us what the seals are doing, for them it's probably fairly unremarkable. It's just their habitat. They're perfectly well adapted to it, and they're using it to their advantage.
Would you like to jump in, Sophie?
Sure. Yes, I think it's hard for us to invert our perspective where we think of, say a cormorant that we see often on the Derwent, and then it plunges in and dives briefly and then comes back with its prey and returns to the surface. And that's what we think of for a diving animal. But what Clive just described, elephant seals can be described as surfacers. So almost all the time underwater, returning occasionally to breathe. And for us, it's like, whoa, what are you doing down there? But I think they dive pretty continuously. It's not like just in the daytime or just in the nighttime. And the deepest dives that we see are actually along the continental slope. So where the shelf is kind of descending into the deep. And particularly the males will be punching down to the seafloor there. So we really don't know a lot about those systems, but we'd have to expect that the energy return is good for that effort. And it's most likely that they're eating fat fish, really lipid-rich fish like ice fish, Antarctic toothfish, maybe octopus, and deep-sea squid. So very clever, extremely well-adapted physiologically predators.
Wonderful. Thank you very much. Our next question comes from Johnny online and is actually for me. So I'm going to take this one. On the slide, a skip in the beat from 2015, we had a consistent loss of ice. Is it safe to say that we've finally reached a point where we can definitively claim that the ice is melting? Sort of. So we know that Antarctic sea ice comes and goes every year. You saw that slide with the beating heart, where in the summer it would melt away and in the winter it would form back up. So yes, ice is melting, but it melts every year. What is more remarkable about what has happened in the last few years is that it hasn't come back as much as it historically did. So this year in particular, we have had outrageously low amounts of sea ice around Antarctica, not just a new record. So we've had 2.5 million less square kilometres of ice than is normal for this time of year, which is a lot. That's almost the size of WA. But the previous record was minus 1 million square kilometres of ice. So 1 million square kilometres of ice less than normal. So this year didn't just beat the record. It didn't just double it. It's 2.5 times larger. So something has changed very fundamentally. Now, describing that as the ice melting is somewhat complicated by the fact that we have this large seasonal cycle. But absolutely, there have been some really dramatic changes. And it's important that we have people like our speakers tonight helping us to understand this system. So, to our in-person audience, our next question. Yes, over there.
Thanks very much for the talk. So great. You talked about the way sea conditions might affect the population of krill, but going back 100 years or so when the whale populations and seal populations were drastically reduced, was that big enough to have any effect on the Southern Ocean, or was it just as a blip?
Well, I have seen some research showing that the loss that whales do represent a really important way for carbon to sink into the deep ocean. So if you imagine just how much carbon is in a whale compared to a microscopic phytoplankton, and if this whale is getting, say, killed by orcas, that I believe they only eat this part of the of the whale, although I'm not an ecologist, and then the rest of it just sinks. And I've seen on Blue Planet some incredible footage of all of these benthic sea creatures coming and feeding on that whale carcass. And so that's huge amounts of carbon that is sinking to the sea floor and won't be rising again for millennia. And so now we have more whales than we did 50 years ago, but still a lot less than it was 500 years ago. And so this is a natural way that carbon could have been removed from the surface of the ocean that we've, in many ways, probably crippled. And so when we think about how we use our marine systems, how we fish, how we might overfish, we should also think about how we might be impairing these natural systems that we really need to fix our system as well, like fix the increase the amount of carbon getting removed. I
think it's a great question, and it is complicated to answer in part because they fudged the numbers. So how many whales were caught has actually been a really big problem to unpick. So it's then difficult for us to kind of back calculate and say, well, what would have been there? But I think Tamara's right in that we have removed a huge portion of biomass. We don't have a good understanding of what the system looked like before. And some populations are recovering very fast. In fact, in Australia, the humpback whales on the east and west coasts are both growing at above the theoretical maximum recovery rate. But then a neighbouring population next door is not recovering at all. And so our understanding of why that is, it's very limited. And we're really looking at these kind of system connections to understand why some areas are recovering and some are not. Did that answer your question?
Yeah, thank you.
I would actually love to hear a follow-up question to that. Do we think this has had an impact on the krill populations now that they don't have to feed quite so many whales?
I think that's called the krill release hypothesis. But again, it's a back of the envelope calculation. It's very hard to validate. But yes, theoretically, releasing that predation pressure released a lot of biomass.
Wow, amazing. Our next question. I think this is for you, Sophie. It comes from Roger online. Or perhaps someone else can take it as well. Is there any evidence that ocean circulating currents are slowing down due to fresh water, and what are the repercussions if that occurs? I thought of you because you mentioned Kathy's work.
I did, yes. So Kathy Gunn next door at CSIRO just published on that topic, and it was looking at repeat surveys from the same area. So, surface to bottom measurements of ocean properties, and in the Ross Sea and Adelie Land, which are two of the bottom water formation regions, they're really seeing measurable change over time from the 50s through the 70s to now. And they are tracing that back to surface freshening. So where you have meltwater near the surface, fresh water is not as dense as salty water. And so the condition at the start of winter really has flow-on effects for how dense water can get by the end of the season. And so the densest water that we may be forming in some areas is not dense enough to go all the way to the seafloor anymore. And so that densest layer is contracting. Ramifications, where deep water sinks, somewhere else in the world, deep water is rising to the surface, and that's the overturning circulation. And we need that to happen into the future because it distributes heat and carbon and keeps the world basically as we know it.
And vital nutrients that fuel other ecosystems. Okay, yes.
Does the increased krill harvesting in the Southern Ocean, have you seen any, or have you seen any change in the carbon pump from krill harvesting?
I love how you're getting all the krill questions as an oceanographer.
Yeah, so unfortunately this isn't my expertise. I think it's related to what Sophie was saying though, how a lot of our calculations are back of the envelope and it can be quite challenging to get realistic estimates. I think so it is important, to note that krill harvesting is carbon that could have potentially sunk, and so it will have an impact, and we can estimate that. Whether or not it's having a significant impact for the whole system, I'm not sure. I suspect it probably isn't, but it's important to consider, like when we evaluate, what is the price of per kilo of krill. I guess what we're talking about today is like, let's also consider the price that this krill, the value of that krill in our natural system, which is a little bit harder to calculate.
Yeah, it's such an important idea to remember to consider the services that these ecosystems provide. There was a symposium in Hobart last week, of Southern Ocean scientists And one of the keynote speakers talked about the value of the carbon that is sequestered in the Southern Ocean. And if you give it a price of 90 euros per tonne, then the Southern Ocean is contributing something like $225 billion a year worth of carbon sequestration. It's quite a big number. Now, our next question comes from online, and I think probably it's for Clive, but all of the panel can have a crack at it as well. Regarding sharing data and climate science knowledge in general, what would you recommend we do in the scientific community to share this knowledge with those who do not have an inherent experience of the scientific method?
Yeah, thank you. That's a really tough question. And I think the short answer perhaps to that is that we need to make the data digestible and the information digestible to a broad part of the community, so not just to scientists. So that means that we can't just leave the information in its raw form. We actually have a responsibility to do some quality control to that and to produce at the end of it, down the line, some products that are easy for people to use and easy for people to assimilate into analyses that they might want to do. And those are simple analyses. But the other thing, of course, is to produce information that's digestible and visual. So giving people access to information where you're displaying the data, not necessarily interpreting the mathematics behind that, because not everybody is a mathematician, myself included. And so, I think one of the most powerful things we can do is to give people information on where, for example, seals are going, both across the ocean and also into the ocean, and to tell them what kind of information they're collecting and why that information is important. So it's a question of making it digestible, I think. And hopefully that's answered the question partly, but I'll hand over to Sophie and Tamara if they'd like to comment.
Well, I think it's a good question and one we increasingly contemplate in our daily lives as scientists, because, we are trained in a scientific method and not necessarily in science communication. So it's an evolving art and a dialogue when you can feed back to us actually, so that's a two-way feedback, how to actually make information more real or more meaningful, how to make it relevant to people's daily lives and the decisions that we make in our daily lives. I think, a lot of us have a climate crisis and thinking, well, what can I do as a small person when I know that actually a lot of the decisions are being made at very big scales. And so it's important for us to all continue that dialogue and the conversation about what it means and what our role is in that picture.
Yeah, I guess from my perspective, I personally follow quite a few different science communicators, like on YouTube. I think there is some incredible ways that they can produce information and communicate really advanced ideas that, about astrophysicists, things that my husband loves that goes over my head, and then yet they're able to distill it down so easily. And so I think there is a lot of innovation going on in science communication, and it's very exciting. And it's great for us too, because we're experts in looking at the data, analysing the science. We're not necessarily experts on the communication aspect. So it's very exciting that we're working more and more with science communicators, new ways to distill that information to people. And personally, I recently published something, and then a YouTuber reached out to me and asked if I'd be willing to let them use my paper to make a video. Unfortunately, I didn't actually have the funding to go ahead with this, but definitely next time if I have an opportunity, I will make sure I have that amount of money sitting there so I can use it, because I know how valuable that can really be to increase the exposure of our work.
Absolutely. Thank you all for that. As Tamara says, we are not professional communicators, we are professional scientists. And this can be such a challenging component of our work. But I think these three have done a fabulous job this evening. Now, we are unfortunately running very close to the end of time, so we have one more question. And I'm sorry, I don't know which of you raised your hand first. Over here, please.
Can you talk to us about the presence of pollution, say, for example, oil pollution on the formation of polynyas and, yeah.
Question was about the impact of pollution, such as oil pollution, on the formation of polynyas. I'm not sure that we actually have an example of that to work with. So, I mean, pollution is certainly a global problem, and Antarctic is no exception. We've got, observations of pollutants in very remote places. In terms of oil spills, I don't know of an example in particular that would translate directly to polynya systems. Thank you.
Well, how about that? We managed to finish on a bit of good news. We don't have any knowledge of oil being spilled in a polynya system. I mean, there's always a chance, but it's a novelty to finish a talk about climate science on a positive note. So we'll wrap up the Q&A there. Now, as we finish up, I hope you can all walk away with a deeper understanding of the role of the Southern Ocean and the critical importance that it plays in our global climate system. The alarming fact is that we're currently observing substantial changes in this vital and remote and wonderful place. We are noting this in the record lows of sea ice extent, the record high temperatures and heat waves across the continent, and, among other things, the striking changes in penguin populations. The chronic lack of observations in the Southern Ocean challenges our ability to understand and predict what is going on. As such, it is more pressing than ever that we have a sustained and coordinated effort to observe the current state of the Southern Ocean, to inform predictions of the future, and to support policies and regulations for the benefit of us all. Our role here tonight was to share with you, and as you leave, I'd like to challenge you to take on the role of sharing the conversations that we've had here with those in your life. Share them around the dinner table, around the water cooler, with friends, with colleagues, with family. Because that is the valuable work that needs to happen from now. That is how we as a society come to a deeper understanding of the issues, the challenges, and the opportunities that we all have. Now, I would like you to join me one last time to thank our speakers for tonight, Dr. Tamara Schlosser, Dr. Clive McMahon, and Dr. Sophie Bestley, for their fabulous talks. As I mentioned at the beginning, this evening's talk is being recorded and will be available on YouTube and SoundCloud soon. And you'll be able to find that via the Islands of Ideas website. To find the latest information about the upcoming events, you can also look at that website. And if you want to, you can subscribe to email reminders about upcoming events. So the next event in our Island of Ideas public talk series is Generation Next, Reimagining a Better Australia. It's next Wednesday, the 30th of August, and you can watch this talk featuring one of Australia's finest economists, Danielle Wood, either online or at our Sandy Bay campus. It's not one to be missed. Until next time, thank you so much for joining us. Good night.